In Golang, managing resources efficiently is key for creating high-performance applications. One way to achieve this is by using resource pools. The sync.Pool is a built-in Go type designed for this purpose. It helps us reuse expensive-to-create objects and reduce the pressure on the garbage collector. What is sync.Pool? It is a pool of temporary objects that can be reused. Reusing objects helps reduce the need for frequent memory allocations, which is particularly useful in high-performance applications. What makes sync.Pool useful? Automatic garbage collection. The objects in the pool may be garbage collected if they are not actively used. Concurrent safe. sync.Pool is safe to use concurrently across multiple Goroutines. How does it work? Suppose there is a pool of objects. Whenever we call the get function on the pool, if the pool has available objects, it returns an object. In case there is no available object in the pool, it allocates a new object using the new function and returns it. The object is then used and returned to the pool using put function. Let's see what the implementation looks like. We begin by creating a pool of reusable objects. Here we simulate a scenario where we frequently need byte slices, which can be expensive to allocate repeatedly. Here we create a pool with a new function, which allocates a byte slice of size 1024 when the pool is empty. This is the initialization function. It returns a slice of bytes. Here we allocate 1 kilobyte slice. We added a print here to understand how it works. The new function is called when there are no slices available. Here is the first call to get function. It fetches a slice of bytes from the pool and returns in this object. This is the first time the pool has been asked for an object. The pool is empty, so it triggers the allocation of a new slice. We added another print here. The object is then used and returned to the pool using put. Now, the pool has a slice that can be reused. When we ask the pool for a slice, it does not have to allocate a new one, so it returns the same slice that was created before. Another print. With put function, the slice is again returned to the pool. Let's run the program. Here we can see an allocation is done for the first get call. For the second get, there is no allocation. It reuses the previously allocated slice. Let's see how multiple Goroutines can use a pool concurrently. We will now extend this example by spawning a large number of Goroutines, each retrieving objects from the pool, using them, and then putting them back. The pool is thread safe, which means it can be accessed by multiple Goroutines without any additional synchronization. Let's remove this code. We will create a large number of Goroutines, about 1,000. Here is the Goroutine. It gets an object from the pool and then puts it back. To simulate some work, let's add a sleep of 100 milliseconds here. Let's put a delay between the creation of Goroutines. We will add a wait group to make the program wait for the Goroutines to finish. We will print a dot when the allocation happens. And when we get the object, we will print a hyphen. Let's change these print ln function to print. We missed calling done on the wait group. Let's do that. Now, when we run the program, we can see a few dots and many hyphens or dashes representing allocations and object fetches respectively. There are a few dots in the beginning, showing a few allocations, and then the slices in the pool are reused. Let's count the allocations in the code. We declare a variable allocation count as 0. In the new function, we increment it with every allocation. At the end, we will put a print showing the number of allocations. Let's run the program again. This time there have been about 12 allocations for 1,000 Goroutines. This is how sync.Pool helps in reducing expensive allocations. While using a pool, we should keep these things in mind. Sync.Pool is great for short-lived objects that are expensive to allocate but frequently reused. Objects in the pool may be garbage collected, so you should not rely on the pool for holding state or long-term storage. And that's it. In this episode, we've demonstrated how to use sync.Pool in Go for efficient resource management. By reusing objects like buffers and slices, you can reduce the overhead of memory allocation and improve the performance of high-load applications. Remember that while sync.Pool can provide significant performance benefits, it should be used wisely based on the needs of your application. I hope this was useful. Like, subscribe, and hit the bell icon for more Go programming tutorials. Thanks for watching and happy coding.